Welcome everyone for the NEECECON 2024. I hope you had a wonderful morning and you have witnessed different company presentations. And we're now in the technical session number 5, which is artificial intelligence and smart cities. Yeah, the second part of smart cities. So the theme for today's conference is the national development through sustainable industrialization. Okay, so there are 5 presenters today, and the topics, all related to AI and smart cities. So from vision language models, we also have large language models. I suppose everyone knows what's Chat GPT, no? So this is one of the natural language processing application. We also have signal processing, so using deep learning and machine learning for signal processing application in machines. We also have digital elevation models for accuracy assessment of satellite images. Perhaps you will be using this in some practical application in the national development. And lastly, we have object detection for university portal smart systems. Okay, so without further ado, first, may we kindly request or remind all the speakers to observe their allocated time. No? So I think it's 15 minutes each, and maybe 1 or 2 questions if there are from the audience. Okay, so first, let me call on the first speaker. So the title of the speaker is Improving Open Vocabulary Object Detection in a Vision Language Model. So this will be presented by a graduate student, Nico Carlo Yabut from UP Diliman.
So good morning, everyone. My name is Nick Yabut, and I'm here to present our paper entitled The Ava World, Improving Open Vocabulary Object Detection in a Vision Language Model. So let's begin. So yesterday, one of the presenters already discussed about object detection, and we're going to take it off from there. So just a quick recap, object detection is a computer vision task involving in identification and localization of objects within an image or video. So we have here an example of a person riding a skateboard, and we can see that the person is identified and localized as well as the skateboard. However, this is a traditional method where we are restricted to identify and localize only the objects that are from a predefined set of categories. So one example of this predefined set of categories is the COCO dataset. We have only 80 classes here. So examples are person, bicycle, car, up to toothbrush. So shown here are the classes that we have for COCO dataset. And in our example, we have identified first person and second skateboard, which are part of this dataset. But what if I want to detect objects beyond those classes? In using our example, what if instead of person, I want to identify him as a skateboarder? And I also want to identify the white shirt, not just the t-shirt, but we have an adjective here, the white shirt. We have also the tight-fitting pants, and also the real. These kind of classes are not part of our base categories or our predefined set of categories. We now introduce the concept of OVOD, or Open Vocabulary Object Detection. This method can detect beyond the predefined categories or classes. It uses the language vocabularies, as you can see here in the diagram of OVOD. We have CL, the big blue here, where we start from the base classes, this small circle here, and then we use the language vocabulary to expand the set of classes that we have for OVOD. One OVOD model that we have right now is an off-the-shelf model called YOLO World. So in YOLO World, you just need to provide the name of the classes that you want the model to identify. However, the main problem here is that you need to do the manual typing of these classes. So we have here our second problem. what if, the first one is what if I want to detect the objects beyond the predefined classes, and the second one is I want to automate everything. I don't want to do the manual typing of the new classes. Can we do that? So in this paper, we propose two methods. The first one is the file Java plus YOLO world. This is a two-model system. And the second method is Java world. This is a one-model system. For file Java plus YOLO world, this is our method one. We employ Java. It is a VLM. It's a vision language model that can interpret an input image and generate descriptive text about the image. So it's like ChatGPT, but we can input an image, and then the model can describe it. So it's like providing the caption for the image. So here's a diagram on how we have obtained these novel classes, or the new set of classes from our image. So first, we have file Java. We have two inputs here. We have the image, that's the first one, and the second one is the prompt, just describe the image. So file Java says, a skateboarder in a white shirt and tight-fitting pants is skateboarding on a rail, and he is riding a skateboard and wearing a cap. So this is the caption generated by file Java, and now we're going to extract the nouns from this caption, and then YOLO world will provide the bounding box, and finally we have the output here, where we overlay the bounding box on the image. So here's another example where I just want to highlight that it can also differentiate that this is a batter and this is the catcher. So from the base class, we can only identify them as persons, but now we can identify them as batter and catcher in this example image. So this method one uses two models, the file Java and YOLO world, and it has this advantage of no training required. So we don't need to fire up GPUs to implement this method. It also does not require data set, which the two advantages translates to money savings. We just need to combine multiple models so that we can get our desired output. So just to check our main problems that we presented earlier, we can detect objects beyond the predefined classes, and second, the no manual typing of new classes is required. Now, for method 2, the name of our method 2 is Java world. The general idea is that, can we teach Java how to do OVOD? We know that Java is a VLM, it's a generative model where it can predict the next word. That's how it provides captions. But can it also predict the bounding boxes of the novel objects? So that's the general idea of this method. Using the method 1 that we presented earlier, we can create a data set to teach OVOD, to teach Java to do OVOD. So basically, we use method 1 to generate the data set for all the Coco classes that we have, and then we are going to use it to train our Java to do OVOD. So here's a diagram of how we could create the synthetic caption. This is a modified method 1 where we start from the base classes, and then we go through each stages from YOLO world to file Java and another file Java to YOLO world to provide the bounding box of the novel set of categories, which will then be part of our data set. So the results of our experiments is shown in the screen. The first method, file Java plus YOLO world, despite no additional training, outperformed both 7B and 13B parameter versions of the Java world. Java words are method 2. It outperforms other generalist VLMs in the score of OVOD for LVs and for the Coco dataset. Shown here our examples that we generated by comparing the vanilla Java, that's the color blue, and Java word 13B, our model. So first one is a picture of a buggy. We can see that the red rectangle here provides a more compact, and it encompasses the whole buggy. Same as Hanso, The third image is a Bible. The fourth image is plow, garbage, and then here vinegar. So in this last image, we can see that the liava, the vanilla liava, the untrained one, cannot detect the vinegar, even though that the image is dark. Our model, Liava World, identified this as, this is the vinegar, this one here. Okay, more examples here. We have, we're going to show some positive, some good predictions and missed predictions. So for the good predictions, we have here the shot glass, the vinegar, the mallet here, even though it is blurred, garbage here, the plow, and the vultures, even though we have many vultures here, the model was able to identify all those vultures, and the vending machine at the back. For some mispredictions, we have here the pipe. The bounding box that was given by the model is this tennis racket, but the actual image is this one, the pipe that is on the mouth of this person. And in this image, we have here helicopter. The bounding box is here, but the helicopter is here. So, and last image for misprediction is the hippopotamus, where the object should be here, the hippopotamus should be here, but the bounding box provided on this area. Now, earlier today, around 20 minutes ago, I took a snapshot of our presentation. So this is a demo of our model. Earlier, I took this picture and then I used our model to provide the bounding boxes if we could detect novel objects in our image. So from the base classes, we were able to identify TV, dining table, and person. So traditional object detection methods provided this TV, person, dining table, and others. But using our model, we have detected the attendees. We have here attendees. This now is screen and not TV. We have here attendees. We have red shirt, tables, and chairs. So that's it for my presentation. We have demonstrated that we could do OVOD for using two methods. The first method is the combination of models without training. And the second one is we could train the Liava model by using the generated captions of our model one. Thank you.
Thank you so much, Mr. Yabut. Do we have any questions from the audience? Anyone? Okay. So 1, 2. Okay, I have a question, Mr. Yabut. It's very interesting that you have this new model or OVOD. Can you please give us some, what do you think, applications that immediately we can apply this?
Okay. So our group in the university is called UCL. So we have the guys there. So sila mga teammates natin. We're actually working on the AGI, Artificial General Intelligence. What we're planning to do is to embed this technology in a robot, for example. That's the ultimate goal of the team. So we have a team for speech, where they convert the speech into words and words into commands so that they could operate the robot. So in this one, we could provide cameras to those robots so they could identify the rare objects even though they are not part of the training. That's the crucial part, because if we deploy something on a robot that only identifies common objects, what if there's a new object in the scene? So it's not going to be identified by traditional object detection method. So that's the importance of this open vocabulary object detection. It would be able to identify objects that is beyond the known classes that we have right now.
Yeah, thank you so much, Mr. Yabut. Okay, so no other questions? So let me give the certificate of appreciation presented to Mr. Nico Carlo Yabot for sharing his invaluable insight and work on improving open vocabulary object detection in a vision language model during the NEECECON 2024, given this 19th day of July 2024 at Novotel Manila Araneta City, Quezon City, Philippines. Signed by Dr. Liu Andrew Tria, the Director of UP EEEI. All right, so we're down on our second presentation for this technical session number 5 on AI and smart cities. So I'm sure, again, you know what's NLP and ChatGPT and other large language models. So we have here a presentation on Itanong DS, a collection of benchmark datasets for downstream natural language processing tasks on select Philippine languages. So this will be presented by Engineer Angel John Adoptante, Project Technical Specialist 1 of Computer Software Division of DOST-ASTI. So let us help him welcome.
Hello. Good morning, everyone. Maagham na araw sa ating lahat. So, once again, I am Engineer Arnold John Adoptante, Science Research Specialist 1 and Project Technical Co-Lead of the Itanong project under the DOST-ASTI. So, today I'll be presenting a paper that has been published in ECL entitled Itanong DS, a collection of benchmark datasets for downstream natural language processing tasks on select Philippine languages. Now, just to give you a briefer, while the Philippines has a lot of or uses a lot of languages in its more than 7,000 islands, Tagalog and Cebuano come out as two of the most prominent and widely used languages in the country. Although it is very much used in our everyday lives by the people of the Philippines, there's still so little data available that can be used for training AI models, particularly large language models. As you all know, if you're familiar with the different large language models existing right now, OpenAI's GPT 3.5, 4, Mistral, Llama, these large language models are trained upon thousands of text and averaging on around terabytes of data, text data on certain languages. So even though we are currently using Tagalog or Filipino and Cebuano in the Philippines, the amount of text data available in the internet are very minimal. That's why we are still considered a low resource language in the AI community. There are actually already existing datasets. Wikitext and Oscar present a collection of Filipino, Tagalog, Cebuano datasets. However, they fail to capture the certain linguistic nuances and the occurring evolution of our languages, especially in what we call code switching. Switching is a linguistic phenomenon in which we switch from one language to another. For example, ganito, nagpe-present ako and then bigla ako mag-switch into English in a very seamless manner. Pero kaya ko rin bumalik into Tagalog. So, very, very few languages our data sets cater to those linguistic nuances. And in fact, these is also one of the prominent research areas of natural language processing in general, code switching. So, as part of our initiative in Itanong and in DOST to cater and to, trailblaze AI research here in the Philippines, we curated a set of benchmark data sets for different natural language processing tasks that include code switch text and cater to the said linguistic nuances. So the scope of this presentation would be how we gathered our data, the pre-processing that we did to make sure these data are clean and suitable for training, our sentiment analysis dataset, part of speech tagging dataset, named entity recognition dataset, some word embedding models that we've also trained and developed, as well as pre-trained language models. Now for the data gathering part, we have collected a multitude of articles, of news articles, open source stories in Tagalog, Cebuano, Taglish. We also did social media posts that are open source that we are authorized, and we have the we are authorized to use, meaning there is no copyright, and these are categorized into two: formal and informal. So formal means formal literature such as research papers, books, and then informal caters to the informal informal sources, stories, social media engagements, things like that. Then these the table 1 shows the total amount of lines gathered per language, so around 5.1 million lines of formal Tagalog text and around 200,000 Cebuano text, and then around more than 3 million lines of Tagalog informal text and almost 2 million lines of informal Cebuano text. Now, given that these were gathered or organized from different sources, we had to do some sort of pre-processing to make sure that these are in our context clean data. So we utilized a pre-processing technique used in the work of Velasco et al. In 2022. So we for the emojis, for the line breaks, URLs, these have corresponding replacements to make sure, not just to make sure that the data is clean, but to also cater to the pattern, or to make sure that everything is in the correct pattern. So for the sentiment analysis dataset, we implemented this topic modeling technique called latent directlet allocation, or LDA, to construct the dataset. So it helped us identify relevant topics within the dataset or within our corpus, ensuring diversity. And then we randomly selected 9,000 sentences from 3 LDA identified languages. Also take note that during our pre-processing, these lines of text have varying lengths. So some phrases or some sentences could be as short as 2 or 3 words, 3 tokens, and some could even reach into paragraphs. So what we did is we only utilized, or we filtered our collected data to make sure that all of the data that we have exceeded at least 3 tokens. Okay. And then upon selecting the 9,000 sentences, we used the OpenAI's GPT 3.5 model to classify 500 phrases into positive, negative, and neutral. And then we used embedding a sentence transformer to generate embeddings of these classifications to check or to capture its nuances. And then we use these embeddings as features for label propagation. So in totality, we have around 3 data sets. So we have a balanced data set of 3,000 each for positive, negative, and neutral. Then 2 unbalanced data sets as shown in the table. So the rationale behind this is there are advantages when you have a balanced data set. That is I think, what we strive for. We want to train our models in our data that is balanced. However, we also cater to those unbalanced data sets for other researchers. Then for post tagging or parts of speech tagging, we adapted a model called SMT post. And then this model was selected as it achieved a higher score of 84.7%. And then in totality, for the word statistics, there were a total of around 71,000 number of words with a vocabulary size of 15,600. Minimum words per sequence was 6, and then a maximum of words per sequence was 26. The dataset exhibited a total count of 3,868 unique parts of speech patterns. And then to get a clearer observation, we extracted the trigrams of each sequence and calculated the frequency distribution of the corresponding post tags. So the most common pattern that recorded on our dataset was FW, 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 which means a foreign word as tagged by SMT post with more than 2,300 occurrences. For NER, or named entity recognition, so we gathered 6,230 data points and used GPT 3.5 model to label the named entity for each word. So for the consistency, we used IOB2 tagging, in which B- was prefixed for the named entity tags where it begins, and I for the subsequent words that are part of the entity. A word that is not named an entity was tagged as O. So here in the figure, we've just shown our prompt on how we did the tagging using GPT 3.5. The researchers, again, we used GPT 3.5, so we ran it at a low temperature of 0.1 to attain a realistic and predictable set of labels. A total of around 143,000 named entities were identified by the model with 6 unique classifications. So the most common was the O tag with almost 125,000 counts. Then we also developed or present a collection of word embeddings in 2 techniques, word-to-vec and fast text, the most common techniques in word embeddings. So these are offered in, again, word-to-vec and fast text, and also in for word-to-vec and fast text, it is available in skipgram and continuous bag of words, with vector sizes ranging from as small as 20 and as large as 300, available in .txt and .bin formats. The team has also conducted pre-training of multiple BERT language models the remaining unlabeled data in both Tagalog and Cebuano. So we just did a 80-20 data split. We trained the model on 80% of the data and then tested it on 20% of the remaining data. We also, in the noteworthy development, the authors pre-trained a BERT Cebuano model. This initiative, to the best of our knowledge at that time, was the first ever attempt to train a BERT-based language model exclusively for Cebuano. So we were helped with some of our interns were actually speak Cebuano, so they were big help in the development of this language models. for the performance of these models in Bert and Roberta, the validation perplexity or the amount of surprise or the metrics that we use to get the performance of these models, the lower the better. So for Tagalog, it's around 8.3. For Cebuano Bert, it's 52.36. Then for Roberta Tagalog, 9.4. And then for Roberta Cebuano, 52.30, around 52.38. For a more detailed explanation, or if you want to further read our paper, it is already available online on the link flash on your screens. And yeah, this concludes my presentation. Thank you very much for listening.
Thank you very much, Engineer Adaptante. So are there any questions, clarifications from the audience? Okay, so, well, perhaps I have one which is similar to the first speaker. What would be the immediate application of the data set that you have researched?
Yeah, the main advantage or the main contribution of this paper is we wanted to provide a benchmark data set for the use of the Filipino researchers on AI and natural language processing. Say you want, most of the benchmark data sets available online or used only cater to the big languages, English, Spanish, French. But given that Tagalog, Filipino, or Cebuano are counted as low research languages, these benchmark datasets will help our researchers benchmark the performances of their languages, thus enhancing the capability and the capability of Tagalog-based and Cebuano-based researches or language models.
Okay. So, thank you so much, Engineer Adaptante. And we would like to present to you the Certificate of Appreciation for sharing your invaluable insight and work on Itanong DS, a collection of benchmark datasets for downstream NLP tasks on select Philippine languages during the NEECECON 2024. Given this day, 19th day of July, at Novotel Manila, Quezon City, Philippines. Signed by Dr. Andrew Tria, Director of UP EEEI. Okay, so I thought you're gonna ask Engineer Adaptante about ChatGPT. No, would it be? Will there be a Philippine, Philippine version of ChatGPT wherein you can just ask whatever language in Philippines, Cebuano, whatever dialect, maybe Longo, no? So I thought you're gonna ask one of these questions. Anyway, let's proceed to the third out of 5 presentations. So we have here the simpler machine learning methods outperform deep learning in motor fault detection. This will be presented by Mr. Antonio Soybriza, Project Senior Technical Specialist of Computer Software Division, DOST-ASTI. Let me help welcome Mr. Briza. Okay, so while waiting for setting up the third presentation, Yeah, so we already witnessed two major applications of AI. We have the computer vision earlier in the first presentation, and then the second one is NLP. So we hope that in the national development through sustainable industrialization, AI would be a front runner. So we know that, for example, the presence of these AI applications such as ChatGPT is a very impactful, in the national development. And for example, in DOST-ASTI has a ongoing research on vehicle detection, traffic management. So using, for example, the first presenter's model, we can have a better transportation. Okay, so I think our third presenter is now ready.
Anyway, I'll just use this. Okay. Yeah. Good morning, everyone. So, thank you for coming to this joint conference organized by EEEI and ASTI. My name is Antonio Cibriza. I'm a project senior technical specialist in ASTI. I'm also with the project ALAM, Automated Labeling Machine, which applies AI models to remote sensing data. So I'm here to present this study that we presented in this conference last February in Osaka. Okay, so this is like a breather from the more technical presentations perhaps that you had earlier. So before I proceed with the meat of the discussion, let me give you the big picture of this presentation so that you can sleep later on. No. So that you can have proper context. So, so in this study, motor fault classification data is collected from 5 identical motors with 4 having synthetically induced fault and 1 healthy. So, yeah. Then stator current signals are collected from each motor under 5 different artificial coupling loads from 0 to 100%. Then time series signals are pre-processed through percentage clipping and log normalization. Then traditional machine learning techniques are done on the pre-processed data. And then convolutional neural network is trained on recurrence plots of motor current signature. Comparison is made with 2 previous studies that use the same data set. The earlier study made use of frequency occurrence plots using convolutional neural networks on them. The other study, succeeding study, used transfer learning on pre-processed data converted to 2D recurrence plots. So the short conclusion is that one machine learning technique outperformed these previous CNN methods, obtaining an accuracy of 93%, and an average F1 precision and recall, beating the first method by 16% and the second method by 12%. So perhaps the main takeaway is that with proper feature engineering, traditional machine learning techniques can beat deep learning methods. This seems to be like a step back from the current trend in machine learning, which is to use deep learning, more complex models. But this shows us the continued relevance of traditional machine learning techniques. Okay, so this is the first study that I mentioned, published in 2020, authored by our facilitator for for this session. So the title is Frequency Occurrence Plot Based CNN for Motor Fault Diagnosis. So this is the motor that they analyzed. So these are the specifications. I will not read through the specifications. So this is a common motor that is used for some machine processes. And then these are the synthetically induced faults done on those motors. One is bearing axis misalignment. Second is stator interturn short circuiting. Then motor rotor strip fault. Then outer ring bearing fault. So those are 4 classes of faults. Then the last class is a healthy motor, meaning to say without a fault. So from those 5 motors, 5 types of motors, 4 with fault and 1 healthy. So we collect stator's current signals. Shown here in the graph are sample signals from the 5 types of motors under different loading. So here you have the 5 classes with 5 loading conditions. And for each class and load, you have 150 time series data are collected. This brings the total time series data to 3,750. So for each of those time series data, it is converted into a Fourier transform, transforming the time series into the frequency domain. And then further preprocessing is done by clipping to 0 to 500 hertz, and then applying also percentile clipping by 90%. Then finally, applying log normalization. These preprocessing stages or steps are necessary in order to highlight perhaps the different characteristics of each time series or its frequency domain representation. Well, this shows the recurrence plots, the preprocessed plots for the 5 types of motors. So sample preprocessed plots for the 5 motors. So from that preprocessed data, we try to convert it into a 2D image using this formula. So essentially, this transforms our preprocessed data into 2-dimensional image. So that was what was done by the first study. So made use of these types of data. So you can imagine 3,750 of these images fed into a CNN in order to classify the different motors. Okay. The second study made use of recurrence plots. So this study also published under ASTI made use of recurrence plots in order to analyze rainfall data, I think. So the task here is to classify the signal level or the rainfall level classification using time series data. So the recurrence plots can be computed using this Python package called PyTS. Recurrence plot is really, it's given by that formula below. So basically, you try to, given a time series, you embed it into a higher dimension using time delays. And then you compare time series with its time delays, and then apply a threshold. And then from there, you can have an idea of which sequences repeat. No? So it's a way of comparing two time series data in visual form. Okay, so I don't have a slide here, but yeah, it's something that I missed. But I was telling you a while ago that there was a second study which used pre-trained data on recurrence plots. So basically, they made use of these kinds of data, but they made use of pre-trained CNN, such as VGG and the like. Okay, I'll come back to that later on, the results of that study later on. But for this study, so these are the data sets that we have. So on the leftmost, you have the discrete Fourier transform. This is the data that will be used by the machine learning models, the traditional machine learning models. The second image is the one that was used by the first study, the earlier study. And then the third image is the one that is used also in this study using a CNN. And then a similar plot is also used by the second study. It's quite confusing. I hope I can clarify that a bit in a while. All right, just to show you the data we are handling for the traditional machine learning models. So there you have the 5 classes. The rows represent the classes, while the columns represent the different loading conditions, 0, 25, 50, 75, and 100. Okay. For the recurrence plot, for the CNN, that use the recurrence plots, this is the architecture that was used. And this is mainly based on this previous study, this one. Okay, so the parameters that were used, the CNN architecture that was used in this study is also the one that we use in our current study. All right, so we go to the result. So listed here are the different machine learning methods that we tried. You have like GBM, KNN, random forest, AdaBoost, MLP, logistic regression, support vector machines, decision tree, extra tree, and naive based. So I think that's 10 machine learning models. Then you can see there the ones with the reference. Those are the previous studies. The pre-trained CNN on FOP, that is the second study that followed up on the study on the original study. Okay. Then the CNN on FOP, that was the original study, the first study. Okay, so what you can see here immediately is that LGBM, KNN, RF, so you have multiple machine learning methods outperforming the CNN methods. You have there 3 CNN methods, right? Then this is the confusion matrix from the 3 studies. The latest study is the one on the rightmost using like GBM, and you can see that visually it stands out as the best performance, the best performing model among the 3. Okay, for details, we have this table. You can just look at the bold values there, which are the best. And from the outset, you can see that Light GBM had a lot of bold values, so which means it performed best in several categories in F1, precision, and recall. And when it is not the best, it performed quite close to the best. So the conclusion here is that, yeah, the principle of parsimony. So to keep it simple, if simpler methods can solve your problem, then perhaps there is no need to complicate your life. just as I'd like to end this sharing, this presentation with an anecdote. Yesterday, we had a presentation, proof of concept presentation with a collaborator presenting a project of ASTI alum. And we presented the results of our initial study, and it showed that, okay, so our study is close to the best performer, but at the same time, it's faster. And the comment of the collaborator, which is a company, is how fast can you produce a result. So many times it's not really, I mean, you're not really after the additional percent, the little additional percent that you can get from complex models, but the speed by which you produce the result. And for that, traditional machine learning models are still of use. They are still very valuable. This ends my presentation. Thank you.
All right. Thank you so much, Mr. Briza. So I hope everyone took note of the presentation. So would you like to ask questions? Anyone? Don't be shy, no? So, okay, so I think wala sigurong questions, no? So, in a way, I don't want to ask a question, but perhaps could you help us, could you give some, other than machine condition monitoring, can it be applied to other applications, these models, these signal processing plus AI?
Well, yeah. A lot of our data is actually time series, right? Many data that we need to process are time series. So this pre-processing that we have done can also be done in other time series data.
Okay, thank you. So we would like to give this certificate of appreciation to you, Mr. Antonio Briza, for sharing your invaluable insight and work on simpler machine learning methods, outperform deep learning in motor fault detection during NEECECON 2024, given this 19th day of July 2024 at Novotel, Quezon City, Philippines. Signed by Dr. Liu Tria, Director of UP EEEI. So we've seen three types of application on AI: computer vision, NLP, and time series data. Okay, so we're down on our second to the last. I hope you're not yet hungry. Okay, so sino bang hindi nakapag-breakfast dito? Okay, so wala naman. Okay. Okay, so for the second to the last presentation is about satellite images. No? So, accuracy assessment of generated high-resolution DEMs using tri-stereo satellite images from ComSat and SkySat over Davao City. So this will be presented to us by Mr. Pocholo Miguel de Lara, Science Research Specialist 1 of Solutions and Services Engineering Division of DOST-ASTI. So without further ado, we have here. Okay, I think. Okay, while setting up, so I would like to know if there are students, graduate students, undergrad students in the room. So can you please raise your hands? Wala. So we have from table number 4 and table number 11. Okay. So very good. So I hope this will be a learning for you guys, no? So without further ado, we have Mr. Lara to present their presentation.
Okay. Thank you, Sir Ed, and to everyone. Good morning. I'm Pocholo Miguel de Lara. I'm currently presenting for Engineer Corinne Ella Morico for her paper under the SAGA project, accuracy assessment of generated high-resolution DEMs using tri-stereo satellite images from COMSAT and SkySat over Davao City. So now, digital elevation models, or DEMs, are digital representation of Earth's surface elevation. So most industries that use DEMs are, for example, who mostly use elevation data for their application. For example, military, communications, infrastructure planning and assessment, geological, disaster risk management, and others. For example, as listed on the presentation. And also, DM is a superset of digital surface model and digital terrain model. So what's the difference between these two? So DSM, or digital surface model, is a digital representation of the Earth's surface model that includes both natural and man-made objects above ground, as compared with DTM, or digital terrain model. It only includes the bare Earth surface, so no trees, no man-made objects. So the project that we are under of is the SAGA project, or the Signal Assessment Using Geospatial Analysis project of the DOST-ASTI, utilizes DEMs for signal propagation mapping and assessment, thus the need for high resolution DEMs, because for signal propagation mapping, we need those terrain to better model signal propagation. SAGAP, DOST SAGAP's, DOST-ASTI satellite subscription includes COMSAT and SkySat. Sorry. So just a brief description between the COMSAT and SkySat. So SkySat, while it is currently in orbit, it has a constellation of 21 satellites in orbit. It has a dimension of 60 by 60 by 95 square centimeter and a mass of 110 kilograms. Now, for the ground resolution of the images, it has a ground resolution for panchromatic of 0.57 to 0.86 meters, depending on the generation of the SkySat used. So it currently has 3 to 4 generations, generation A, B, and 2 generations of C. For the spectral bands, both SkySat and COMSAT-3 have spectral bands of red, green, blue, and near-infrared. Well, actually, if we include panchromatic, they both have. And SkySat has a revisit time of 4 to 5 days. COMSAT-3, on the other hand, is a little big. It has a dimension of 3.5 to 2 meters and a mass of 980 kilograms. And it has a ground resolution of 0.5 and 0.7 meters. And same with SkySat, it has the same spectral bands and has a revisit time of 3 to 4 days. Now, I will discuss a bit about the images that we used for our study. For the COMSAT-3, we used 6 level 1O. Later, I will discuss what is level 1IO. 6 level 1IO image captures to cover the 100 square kilometer of area of interest of Davao City, Philippines. So these images were captured on April 14, 2023. Now for the SkySat, you can see at the right picture, we used 66 SkySat scene image captures to cover 25 square kilometer AOI of Davao City. Well, it is much smaller compared to the COMSAT area. The SkySat were captured on June 29, 2023. Now, a brief description. COMSAT-3 has a single instrument called AEISS, or the Advanced Electronic Image Scanning System, with a resolution of 0.7. Well, also as discussed earlier, 0.7 resolution panchromatic. Now, for the different processing levels offered by COMSAT-3, we have 1R, 1O, and 1G. So 1R meaning the images are corrected for radiometric and sensor distortions. And 1O, or as they call it, ortho-ready, are images which includes all corrections applied to 1R with additional corrections for geometric distortions, optical distortions, and terrain effects using the average height over the region. Now, on the other hand, 1G includes all the corrections applied to 1R and 1O, but using the corrections from SRTM. Now, SkySat has three imagery products available in the form of scene, collect, and video. Now, scene is an individual scene within a strip of approximately 1 by 2.5 square kilometer, while collect is a collection of around 60 SkySat scenes of an area of 20 by 5.9 square kilometer. And video is a full motion video collected within 30 to 120 seconds by a single camera. Now, for the DM workflow chart for the ComSat-3 and SkySat images, we used PCI Geomatica to generate these high-resolution DEMs and using at least 3 images for tri-stereo DEM generation. So, for example, for the ComSat-3, we first pan-sharpen the multispectral images, then push through with the DM generation. Now, for the SkySat, we first generated an ortho-rectified image, then proceeded with the DM generation. For both the ComSat-3 and SkySat-3, we use an additional data for better overlap of images. We used AW3D-DM and the S3 World Imagery. Now, this is the generated DMs that we have done for the ComSat-3 and the SkySat. Now, for the SkySat, it is part of the southwest part of the ComSat-3. Well, the ComSat-3 is a much larger, has a much larger area. So, just for comparison, you can see that the SkySat is just on the southern part of the ComSat-3 DM. Now, if we're looking at the profile made by the Transect AA on the top plot, we can see very minimal deviations between the 3 DMs, ComSat-3, SkySat, and the SRTM 1 arcsecond DM. But if we look at the second transect line, BB, wherein this is mostly located on the urban areas of the Davao City, there we can see a large deviation between SRTM and the 2 generated DMs. One most reason for this is the difference in acquisition dates. For example, SRTM is a project done in the early 2000s. So compare that with the acquisition dates with the ComSat-3 and SkySat, maybe there is a difference in the urban areas. Maybe there are more buildings or houses that have been constructed at that area. Also, there's also the difference between the resolution. ComSat-3 and SkySat have a sub-meter resolution, while SRTM have a 30-meter resolution, a ground resolution. We also got the difference between the ComSat-3 and the SkySat versus the SRTM. If we are looking at the plot or the images, the green areas comprises of low errors, while other colors have higher errors or difference in elevations. Now, for the table 1, ComSat-3, due to its larger area, have a more data points consisting of at least 98,000 and having a mean error of 4.3982 and a root mean square error of 6.2699 and a percent correlation coefficient with SRTM of 0.9695, so which means it has a good correlation with SRTM, but a bit of error, mainly due to the difference in resolution and the difference in acquisition dates. Now, for the SkySat, due to its smaller area, it has 25,409 data points and has a mean error of 3.9398 and an root mean square error of 6.04836 meters and a present correlation of 0.9738. So both areas, both generated EMs having a good correlations. Excuse me. Now for the next comparison, we compare the generated DMs with NAMRIA spot elevation. We just got these spot elevations from NAMRIA's geoportal. For COMSAT 3, we used 41 spot elevations, and we calculated a mean error of 2.7766 meters and a root mean square error of 4.5836 and a present correlation coefficient of 0.9918. Now for the SkySat, we used 11 data points, 11 spot elevation points with a mean error of 3.2274 and a root mean square error of 5.5705 and a present correlation coefficient of 0.9953. Now for conclusions, we generated both high resolution DMs for COMSAT 3 and SkySat images showing strong correlation and approximately low error values after comparison with publicly available datasets containing relevant elevation information. But I would like to take note that due to the difference in acquisition dates and the resolution, there is a bit of errors based on what we saw earlier. Now, to generate high-resolution DEMs from COMSAT 3 and SkySat, we can either use panchromatic images directly, or we can pan-sharpen those multispectral images using the panchromatic images from both COMSAT 3 and SkySat. Now, additionally, additional datasets were incorporated. For example, earlier, we used AW3M DM and the S3 world image to better overlap the processed satellite images. Now, for future work, further assessment of the accuracy of the generated high-resolution DMs are needed. For example, we need to conduct ground truthing activities. For example, more GPS campaign or precise leveling on the ground, or to use NAMRIA's first and second level order benchmarks around the study areas for comparison. So these first and second order benchmarks are also ground truth based on NAMRIA's measurements. And after further validation, the goal would be for the DM extraction process to discussed in this study to be applied to other area of interest, as SAGAP also generated DMs for other areas. For example, we have generated in Iloilo, General Santos, Quezon City. So hopefully we could use this, what we have done in this paper and what we have suggested for future work on other area of interest. And for this is our references for our study, and thank you for listening.
Yun. Thank you so much, Mr. Delara. So, we would like to hear from the audience if you have some comments or questions. Who are from Davao City? So I think we can ask someone. Okay, so walang nag-raise ng hand, no? From Davao City, no? But since I'm from Davao City, so I can ask question. So no, it's not a question, but you see the maybe the importance of accuracy assessment, no, in the satellite images, and so what would be your future future works on, for example, applying AI in the accuracy assessment?
Uh, Currently, we have not delved on the use of AI, but currently we are discussing on developing low-cost GPS receivers for further validation because I think at best when it comes to this elevation or at least geodetic problems, it is most important to hold ground truthing activities because it is different when you're using satellite images or any remote sensing capabilities as compared with ground truthing activities. So for example, with this, aside from using SRTM, we need to hold these ground truthing activities, for example, holding precise leveling or GPS campaigns. As for now, we're currently, as discussed earlier, developing low-cost GPS receiver. So then we can use that to do ground truthing activities in Davao areas and to other area of interest based on what we have generated in the Saga project.
Thank you, Mr. Lara, for your presentation. So we would like to give the certificate of appreciation to you, Mr. Lara, for sharing your invaluable insight and work on accuracy assessment of generated high-resolution DEMs using tri-stereo satellite images from ComSat and SkySat over Davao City during NEECECON 2024, given this 19th day of July 2024 at Novotel, Quezon City, Philippines. So this is signed by Director Liu Tria, Director of UP EEEI. There you go for the second to the last. And we're down to the last presentation. But before we proceed, you see the importance of accuracy measurement on, especially in the smart city. No? We're in the technical session number 5. And like any other technology, accuracy assessment is very important. So we were taken, outside the Earth, no? So with the satellite images. And earlier, there's also accuracy measurement in the machines for Industry 4.0. And for our last presentation, we're not just taken outside the Earth, but we are taken into the universe, no? Sorry, it's not the universe, but the university portal pala, no? So university portal augmented with smart systems. So they call it the UPass, no? So this will be presented by graduate students, Ms. Iza Halandoni or John Rick Mirando.
Hello, mic test. Ito yung next. Okay. Mic test. Hello. Yes, hello. Okay. Let me just test. Ay, hindi kita. Yun yung laser. Laser. Okay, anyway. Okay, so good morning, everyone. I'm Iza, and on behalf of our team, allow me to present UPass. So UPass, which stands for University Portals Augmented with Smart System, is a project under UP and is led by Dr. Atienza and Dr. Randley Cojote with the aim of improving the security of our university. Specifically, it aims to improve the sticker system currently being implemented by UP. Now, while the sticker system is a widely used or a system to regulate vehicles entering certain premises, it does have its own disadvantages in a sense that one, manual inspection of these stickers is potentially or can potentially slow down traffic and is relatively time consuming. So as you can see in this image here, you can imagine a guard stopping an incoming vehicle or let's say incoming vehicles in order to check one by one if those vehicles have a sticker. So And actually, to further elaborate my point, allow me to briefly narrate an experience, no, wherein the gate closest to Triple EI, which is the same gate that where our system is currently being deployed, is the Velasquez gate. So kung nakadaan na po kayo doon, and the guards monitoring that gate used to be very strict in a sense that if wala po kayong UP sticker, you will not be allowed to enter. Despite this, some drivers still try to negotiate with the guards that maybe with just their UP ID, they could be allowed entry. However, despite that, of course, the guard still says no. And to be fair, we really cannot blame those guards because they're just doing their job. But at the same time, we also understand the concern of the students, the UP staff, especially those whose workplace is just near the Velasquez gate. But because of this, will be or were greatly inconvenienced. Moreover, that negotiation between the driver and the guards is more often than not what causes the traffic dun po sa Velasquez gate. So here's where UPass comes in. We're in, as part of the team, we try to alleviate some of those concerns or those issues by assisting, not replacing our guards in order to improve their overall efficiency and therefore the overall security of UP. And shown here is our current setup, dun po again sa Velasquez Gate, wherein on the left side, you can see our data cabinet being installed. Yung black po na nasa likod. And on the lower left of that same image is yung camera po namin, which is the same camera na makikita niyo po dun sa right. And on that right image is also our monitor, which displays the current plate predictions based on the vehicles na nakikita po nung camera. And shown here is our full system diagram, wherein we first capture images of vehicles through the camera, and those images are being passed on to the Jetson or Nano, which is an edge device developed by NVIDIA, capable of hosting as well as running AI models. And yung predictions po doon will be passed to the monitor, the same monitor I showed earlier, as well as an in-house server where all our data are currently stored. And that data can be accessed by our web app. Now, the web app is still under development, but its main purpose is to act as an interface for an admin to track down data records, yung mga records po na nasa database, but can also be used for demo purposes, and only then will it be viewable by the public. Now, I mentioned AI models earlier, and since this is an AI talk, what models did we use then to build our system? To answer my own question, we actually used two state-of-the-art models, the YOLO V8X for both vehicle and plate detection, as well as Parsec, which is actually a network that was developed by one of Dr. Atienza's grad students, Sir Darwin Bautista. And shown here is our model diagram naman po. So given an image, the YOLO V8 predicts two sets of bounding box coordinates, one for the vehicle and one for the plate. So yung TLX, TLY, BRX, BRY po doon corresponds to the top left and bottom right XY coordinates of those bounding boxes. And from there, we extract the plate area from the image using the given plate box coordinates po ng YOLO. And then that extracted plate will then be passed on to Parsec, which then predicts the corresponding plate text naman. And the lower left, you can see our sample output. Now, these models are already pre-trained by the proponents working on YOLO V8 and Parsec. However, they were trained using data sets that aren't fit for our task. So with that, we'd need to have or to look for publicly available data sets with enough data points for our task naman. And that is because neural models generally require extensive amounts of data for training in order to predict accurately. So we did just that. We found multiple data sets for vehicle detection as well as some for plate detection. Specifically, the Kitty data set as well as the CCPD, or the Chinese City Parking Dataset for vehicle and plate detection respectively. However, we did encounter some challenges with these public datasets. Specifically for vehicle detection, the annotated vehicles do not include some of our local vehicles like the jeepneys, the tricycles, and this is because those data sets are usually, or most of those data sets are usually created by universities or organizations from Western countries. So as you can see here on the top left, it mostly shows yung mga private vehicles po, cars, sedans. They do have some buses and trucks, but of course, no jeepneys and no tricycles. Kasi yung dataset po nila only consists of vehicles commonly seen in Western countries. And for the plate naman, of course, the license plate do not follow the Philippine standard format. In our example here, it follows China's standard registration plate format because it's a Chinese data set. So if we only build a system based off of models that are only trained with this public data set, naturally our system would actually produce relatively poor results or bad performance. And because of that, the team decided that we should create our own data set. And we actually did, or actually are currently also still trying to expand our data set. And shown here are just some samples of our some vehicles in our data set. So we include both commonly annotated vehicles, like the private cars, motorcycles, and bicycles, and we also include local vehicles like our PUVs, like the jeepneys, the tricycles, and actually electric vehicles like the e-bikes and the e-trikes. And we annotate both the vehicle and their license plates if available. So how did we do it? To create our data set, we used a semi-automated labeling strategy to speed up the annotation process. So how this works is that we first manually annotate a set of images, and then we use that set to fine-tune our model, which we then use to generate initial predictions or initial annotations, which the annotators will then just refine. It's just a rinse and repeat process wherein the refined annotations are then used to fine-tune the model, to generate annotations naman of another set of data set, and so on and so forth. And the good thing about this is that with repeated training or further fine-tuning, we would be able to, our model gets more and more accurate and will produce better and better annotations, and hopefully later will translate to the lesser need for to refine the annotations. So hopefully in the near future, we'll be able to transition to a fully automated labeling strategy. Now, okay, so we do admit that due to the sensitivity of our data and the concerns of privacy, the team noted early on that we should look for a tool that can be deployed locally, but at the same time can be accessed by multiple annotators. That doesn't require them to be in the lab, for an example. And fortunately for us, we're able to find such a tool, which is the computer vision annotation tool, which is a full support for local deployment and self-hosting. So hindi po kami sponsored, no? Pero we just like to share it to everyone in case there are others here who are facing the same concerns as us. And shown here is our the current system results. So from an accuracy of 10.2, we were able to improve it to 61.9% after repeated fine-tuning. And by the way, the accuracy, we define accuracy here as whether or not our system was able to detect the vehicles and also give correct plate text predictions versus the ground truth. And for vehicles that do not have license plates, such as the bicycles, the system must still be able to detect them, but at the same time, just give a plate prediction of none. And below are our model-specific results, where we achieve an F1 score of 96.1 for the vehicle, which is already relatively high, a 77.1% for plate prediction to an overall 86.9 F1 score for YOLO V8X, as well as an accuracy of 86.5 for plate recognition from Parsec. So as you notice, the F1 score of our plate detection is actually relatively lower compared to other scores, and this is likely due to the low recall scores, which can be attributed to actually just a few instances of our plate bounding boxes compared to the vehicle. And actually, currently, we're thinking that these scores is what's causing the bottleneck in our system accuracy. So currently, we're still in the process of further annotating more data in order to improve our system results. And shown here is just a brief demo, how to play, showcasing the current capabilities of our system.
Thank you for the presentation. So may I ask, what is the size of the data set that you use for UPass?
Okay, so Okay, I'll answer the question first. So currently, we actually have 2 days worth of data, which is about 26,000 images, and we use that to train our, actually 28%, around 8 or 10% of that, so 2,000 is used for validation, and around 26 is used for training. So we use it to train both the detection models as well as the plate text predictions.
Thank you, thank you.
Okay, so as you can see, it was able to detect the vehicle, a private vehicle, and I think the next was a jeep. Meron po kaming live demo sa labas, if in case. But that's all. Thank you very much for listening. Then that was UPass.
Very good. So now you can go to UP and you don't need to. Can you still ask the guard? I mean, the guard would still ask the drivers.
UPass is still not fully implemented, so it's still in the experimental phase. But maybe in the future, who knows? Okay, so just to answer his question, which was if the guards would still need to ask the drivers. So currently, UPass is still not fully implemented. It's still in experimental phase. As you can see, yung accuracy po namin nasa 60% pa lang. But maybe in the future, depende po.
Very good. So hopefully in the future, no, so we can enter UP smoothly. So to give you this certificate of appreciation to Ms. Iza Janantoni for sharing her valuable insight and work on UPass University portals augmented with smart systems during the NEECECON 2024, given this day, 19th of July 2024 at Novotel QC. So signed by Dr. Liu Tria, Director of UP EEEI. Hey. So yun, we're finished with the last presenter, and for this technical session number 5, and we hope that the students over there, you learned a lot, no, from the presentations, and for all who attended this session. So time check, we're about time, no, the time that allocated for this session. Thank you so much, and signing off, Eduardo Pira Jr., DOST-ASTI. Thank you.